So, welcome all. Today again we will continue with our quest of the how to design the energy absorbing materials. Okay. So, last time we were looking into the characteristics of the energy absorber, okay, and we have defined the reaction, okay, and we were trying to give, or we were trying to analyze what is the average reaction energy that is being absorbed by the energy absorbing materials. Okay. So, we will continue with the same thing and we will be also looking into the different aspects. Okay. So, the next thing to define is the load fluctuation factor. Okay. So, we will define one more quantity that is called the load fluctuation factor. Okay. So, as we defined in the last class, okay, we defined the reaction load, okay, the average reaction load and the maximum reaction load. Okay. We defined the stroke also, and we defined the mass and the total volume measure. Okay. So, the stroke, as you remember, we defined as the displacement of the energy absorber at the load application point. Okay. The reaction load is the dynamic resisting load developed by the energy absorber, and it is given as a function of the stroke. Average reaction load we defined as an integrated area of the reaction stroke curve, and it is being averaged out over the entire stroke length. Okay. So, similarly we are defining the load fluctuation factor. So, the load fluctuation factor is defined in terms of R max, the maximum reaction load, and the average reaction load. Okay. So, it gives us a sense of how the load is being absorbed by the energy absorber. Okay. So, it measures the deviation from an ideal square wave form load characteristics. Okay. Next quantity is the bulk density. Bulk density rho is the mass per unit apparent volume. Okay. And the total absorbed energy of the energy absorber is given by the entire average loading times the stroke. Okay. Okay. Where ED and ES are the dissipated and the stored energies. Okay. ED is the dissipated energy in the energy absorber, and ES is the stored energy in the energy absorber. Okay. So, this 5 quantities we have defined. Okay. So, we defined the stroke, okay, the displacement at the load application point, the reaction load is the dynamic resistance developed by the energy absorber, the average reaction load is the load considered over the total area, okay, averaged out by the stroke. Okay. R max is the maximum reaction load. Okay. The load fluctuation factor is the ratio of the R max divided by the R naught, the maximum divided by the average loading. Okay. Bulk density rho, mass per apparent volume, and total energy absorbed. Okay. That is we defined in terms of the average reaction energy and the stroke, okay, where E is the combination of the dissipated and the stored energy. Okay. So, this 5 characteristics we have defined, and we will try to use this quantities in order to measure the efficiency of an energy absorber. The next factor to define is the damping factor alpha. Okay. So, damping factor is the ratio of the energy dissipated to the total energy absorbed. Okay. So, let us say E is the total energy, okay, and it is divided into 2 parts, dissipated plus stored. Okay. So, the damping factor is the ratio of the ED divided by E total, okay, because this is the absorbed energy and this is the stored energy. So, the absorbed energy gives us a sense of the damping factor. Energy density EV measures the energy absorbed per unit of the apparent initial volume. Okay. So, this quantity is used in order to compare the different energy absorbers. Okay. It is used to see the efficiency of one energy absorber versus the other energy absorber. Okay. And this is nothing but the total energy divided by the apparent initial volume of the energy absorber. Okay. So, the other quantity that we also looked through was the specific energy, and this was the energy absorbed per unit mass. Okay. So, energy absorption density, when we talk about density, we know that we are talking in the volumetric sense, and when we talk about specific energy, we are talking in terms of the mass sense. Okay. So, these are the two distinctions. Okay. One is in the volume sense and other is in the mass sense. Okay. And both quantities can be used in order to denote the efficiency of one energy absorber over the other energy absorber. Okay. Okay. So, continuing ahead, for some energy absorbers an axial deformation process, okay, like the tensile deformation, compressive deformation or sometimes buckling is involved. Okay. The consideration of the initial length and the apparent cross section areas, okay, where V equals to A leads to the definition of the following meaningful parameters. Okay. Let us say we are dealing with an energy absorber, okay, where it absorbs energy, okay, in the form of crushing. Okay. The layer crushes out. Okay. So, there is an axial deformation occurring. Okay. So, here we are defining some terms like length, okay, initial length L naught and initial cross section area A naught. Okay. So, the apparent stress or pressure is the reaction load per unit cross sectional area. Okay. So, sigma, the apparent stress is reaction load, okay, per unit the initial area. The average apparent stress is given by the R naught, okay, okay, divided by the initial area. Okay. So, this is the apparent stress, okay, or stress at any given location, and this one gives the stress over the entire regime. Okay. So, here R is given at a certain location and here R is R not used is the average one. Okay. So, this is the two distinctions here. Okay. So, the apparent total strain energy is the ratio of the deflection of the initial length. Okay. The stroke efficiency is given by epsilon max or x max divided by the L. Okay. So, the maximum stroke divided by the total length, okay. And it is the maximum admissible apparent strain, okay, that is before uncontrolled deformation, failure or unacceptable fluctuation occurs. Okay. So, similarly sigma naught, okay, the average apparent stress can also be written in terms of the volumetric energy, okay, divided by the total strain. Okay. And the stroke energy is also defined sometimes by the ratio of the average reaction load divided by the maximum reaction load. Okay. So, these terms are basically used in order to compare the efficiency of the system, efficiency of the energy absorbing system. So, moving ahead into the energy absorption characteristics. Okay. So, a valuable energy absorber should essentially present a high specific energy and a high damping factor. What does it mean? High specific energy. Okay. So, the definition of the specific energy we looked here. Okay. So, as we have seen in the previous classes also, this is the measure of the total energy absorbed, okay, per unit mass. Okay. So, the amount of energy absorbing material used. Okay. So, let us say this is the amount of energy absorbing material used. So, this is the mass total of the system and the total energy absorbed is E. Okay. So, the specific energy, okay, the energy absorbed per unit mass becomes E divided by M total. Okay. And when it is considered in terms of volume, then it becomes the energy density. Okay. Okay. So, the energy absorbed per unit mass, okay, if it is more, then it means if it is, let us say EA is 100 for a system and EA is 80 for a system. Okay. So, this system, the first one, okay, which is absorbing more amount of total energy per unit mass is an efficient system than the latter one. Okay. So, higher the value of the specific energy, the better the energy absorbing system is. Okay. The other factor that is being used is the damping factor. Okay. So, the damping factor we defined as the energy dissipated divided by the total energy, E total. Okay. So, more the amount of energy is dissipated, the better the energy absorption system is. Okay. So, the efficiency of the energy system, energy absorber is defined in terms of specific energy as well as the damping factor also. Okay. So, energy absorption devices with a damping factor close to unity exhibit specific energies EM in the range of 50 to 50,000 joules. Other typical range of characteristic parameters are, so these are the some of the commonly available ranges. So, energy density, EV, okay. Again, when we are talking about the energy density, it means that we are dividing by the volume, okay. When we are using specific energies, we know that we are dividing the energy by the mass, okay. So, if the damping factor is close to unity, it means that the total energy in the system is dissipated, okay. This factor becomes 1, it means that E, the total energy, okay, becomes close to the dissipated energy, okay. Total absorbed energy becomes same as the dissipated energy, it means that the stored energy is minimal, okay. So, this is a very efficient system, and in this case the energy absorbed per unit mass is in the range of 50 to 50,000, 500 to 50,000 joules, okay. Energy density, that is the total energy divided by the volume, is in the range of this number. Bulk density is 200 to 9,000 kg per cubic meter. So, apparent average stress is around 10 to 5,000 bars, and the stroke efficiency is 10 to 90%. Okay. Here we look into the energy characteristic curves. Okay. So, the first one is the typical load deflection curves or the stress strain curves. Okay. So, we have seen this thing a lot of times. Okay. So, more is the energy absorbing material should have a higher plateau region. Okay. So, this signature is shown here. So, the total amount of absorbed energy is the area, total area under this curve. Okay. So, this part where it remains in the elastic range, okay, this gives the stored energy, and this region gives the plastic energy. Okay. And this is a curve of the energy versus the stroke length. Okay. So, this is a typical energy deflection curves or energy density strain curve also. Okay. So, these are the typical signatures of energy absorbing materials, the high plateau region, the energy absorbing region, and these are the sum of the numbers associated with the energy absorption, be it a specific energy or the energy density. Okay. And this gives the efficiency of one energy absorbing system over the another system. Moving ahead. So, now we are looking into the reusable devices, okay, or multi-cycle devices. Okay. Let us say we have designed a bulletproof jacket. Okay. So, a bulletproof jacket, when we design it, it cannot be for just one use. Okay. It cannot be for just one use event. Okay. It has to sustain multiple impacts. Okay. It has to sustain certain number of bullet injuries. Okay. Same is in the case of other devices also, okay, like the packaging materials and all. Okay. So, they should be reusable. Okay. So, we will look into the reusability criteria. In some cases, the energy absorbers are not reusable, okay, like in case of a vehicle impact. If a vehicle impact occurs and the front part and the back part crushes out, okay, then we have to replace these parts. Okay. So, there is no question of multi-cycle use. Okay. We have to replace the entire thing. Okay. But in case of bullet protections, okay, or packaging, okay, there is a need to have a multi-cycle use, okay, or the reusable devices. Okay. So, the absorbing devices classed here are those in which the incoming energy is mainly or fully converted into heat or escaping fluid kinetic energy by a friction or controlled flow process. Okay. As such devices do not involve a destructive process, they can be used in a number of impact cycles. Okay. So, they can be used in a multiple phases. Okay. So, the following types of energy absorber belong to this category. Okay. Solid friction types, viscous friction types, or fluid discharge types, okay, like in a water cell. Okay. So, here the idea is that the total incoming energy, okay, whatever energy is imparted to this system, they are mainly converted into heat or heat model by a friction or friction process. Okay. And this type of does not involve a destructive process. Okay. In this type of devices, this type of region is not there. Okay. So, they can be used in a number of times. Okay. So, we will look into the instances of this multi-cycle usage energy absorbers. Okay. There are other class of devices called one shot or destructive devices. Okay. So, in this class what happens is that the device contains the incoming energy, and this incoming energy is fully converted to heat through a permanent deformation process, okay, like this plateau formation. Okay. So, there is a permanent deformation phase. Okay. So, such devices can be used for light impacts. Okay. Let us say this region remains till here only, okay, a light impact occurs. Okay. With the rated capacity range, most energy absorption devices belong to this category of relatively simpler design with a wide variety of possible dissipative energies. Okay. So, their main function is through a ductile deformation process, okay, this high plateau region process. Okay. So, these are called the one shot devices. Okay. So, examples of the one shot devices are the function in the extension mode. So, uniaxial tension of steel rods and cables, nylon ropes, etc., member tension of compressed fluid filled tubes or other closed envelopes. Okay. So, all these devices deform in a uniaxial type of behavior. Okay. So, the impact occurs and there is a crushing of the faces. Okay. So, either the uniaxial crushing will occur, okay, or sometimes they are taut also, and there the uniaxial tension occurs. Okay. So, either there will be an extension mode or a compression mode, okay, like the massive bumpers made of steel, copper, aluminum and different metals or even different plastics, cellular bodies like metal sponge, plastic foam, balsa wood. Okay. Depend upon whether or not the full cross section is concerned, the compression process will be referred to as crushing or punching. Okay. So, as we have seen here, okay, if an impact occurs, this entire things will be crushed. Okay. Or if the cross sectional area is more, then there will be a punching type of deformation, very localized type of deformation will occur. Okay. So, bending mode, so normal bending mode of beams and plates will occur. Okay. So, these are the different modes of deformation of a one shot devices, okay, which normally deform in case of a ductile type of deformation. Moving ahead. So, there are other modes also, okay, like shearing mode is there and there is mixed mode is also there. Okay. The one shot devices may fail in case of shear mode also, or a combination of a bending mode and bending mode plus a compressive or tensile mode, or any other combination of this mode is there. Okay. So, normally the shearing mode occurs, okay, there is a fracture involved. Okay. This process is applicable to an even wide range of materials which may be of brittle nature. Okay. So, in case of a ductile type of material, what we will see is that a compressive crushing or a bending type of failure will occur. Okay. If the material is ductile, if the material is brittle type of material, then there are chances of occurring a fracture process. Okay. So, this process, okay, so it covers an even wide range of materials, okay, which are of brittle nature. Okay. But they occur in the overall compression mode, okay, like metal tube fragmentation, metal cutting, crushing of brittle plastic honeycomb systems and crushing or punching of cellular concrete or refractory material occurs. Okay. So, in these cases our fracture mode comes into picture. Okay. So, we have looked into multi-cycle mode, okay, where the energy is converted into the heat energy via a friction or a escaping type of process, okay, a fluid type of process. Then we have looked into the one shot destructive modes in which the ductile deformation occurs, okay, and if the ductile deformation is occurring, then it can be considered of tensile mode, compression mode or bending mode, okay, where there is a large plateau formation and the energy is absorbed by this formation of this plateau. Okay. So, the other type of deformation that can occur is the fracturing process in which the brittle materials are involved, okay, and different instances of this brittle process are given here, okay, like metal tube fragmentation, metal cutting, crushing of brittle plastic honeycomb structure, and crushing or punching of cellular concretes. Okay. So, in this case the fracturing process occurs, okay, which is in turn made up of a shear or a mixed mode failure. Okay. So, we will be looking into some examples. Okay. So, let us say we have a stainless steel energy absorbing rod. Okay. We have a rod made up of stainless steel. Okay. This is an SS rod and it is used in a pipe whip restraint. Okay. So, it is used as a strut material. Okay. The rod undergoes a displacement stroke of 0.25 meters and the average resisting load developed is 4500 Newton, 4500 Newton. Calculate the total energy absorbed by the rod during impact. Okay. So, the total energy absorbed we have seen, it is given by the expression the average reaction force times the stroke length. Okay. So, the total energy absorption by this system is given by this particular expression. Okay. Similarly, the other systems, let us say we have a cylindrical copper bumper, okay, which is used to absorb energy during mechanical equipment failure. Okay. So, there is some sort of a bumper, okay, where if an impact occurs it will deform, okay, in this fashion. Okay. The mass of the bumper is 3.5 kgs. Okay. The total energy absorbed is found to be this number. Okay. So, what is the specific energy absorbed by this number? Okay. So, basically we are trying to calculate a parameter, okay, where we can find out the efficiency of the system. Okay. So, the total energy divided by the total mass gives the specific energy. Okay. Similarly, if the volume was given here, okay, we could have calculated the EV, okay, that is nothing but the total energy divided by the total volume. Okay. So, in this way the two numbers EV and EM, the specific energy and the volumetric energy, can be used to calculate the efficiency of the system. Okay. Similarly, if we knew the dissipated energy and the total energy, we could have calculated the alpha, okay, the damping factor of the systems, okay, and using this 2-3 parameters, okay, we can comment on the efficiency of this energy absorption systems. Okay. So, this is how we are using whatever we have learned previously. Okay. So, we will continue with one more example. In this examples, now we are comparing two materials, okay, that has to be used as a pipe whip restraint. Okay. Basically, it has to be used as an energy absorber and there are two competing materials. Okay. So, material A, it has an annealed SS rod, okay. So, this is an SS rod and material B is some sort of a cellular concrete, basically it is a foam type of concrete is there. Okay. So, average stress given by 3500 bar in case of steel and 80 bars in case of concrete. Maximum strain of steel is 0.35, maximum strain occurred in the cellular concrete is 0.4. Density of the steel, the SS rod is 7900 kg per cubic meter. Density of this cellular concrete, okay, this is lesser than the conventional concrete. The conventional concrete has a density of around 2400 kg per cubic meter, but this is a, since it is a cellular concrete, it has a lower density. Okay. So, now we are asked to calculate the energy densities for both materials. We are asked to compute the specific energy for both the materials. Okay. We have to comment which material is more efficient, okay, looking into the unit mass criteria, and we have to also comment which one is more efficient for a space constraint design, basically the volumetric criteria. Okay. So, we will look into the solution. So, EV we will try to calculate. Okay. So, EV for material A and material B we will try to calculate. Okay. First of all, we will look into the stress. Okay. So, the stress we will calculate using this expression. So, the EV we will take the, for material A and this is material B. Okay. So, EV is given by the average stress sigma naught times the strain, okay, and for this material B again EV is given by average stress and the strain. So, in this case the first stress is 3500 the first stress is 3500 times the strain, okay. And in the second stress, the average stress here, this average stress is 3500 and the strain is 0.35, okay. And for the case B, it is 80 times 0.4, okay. So, obviously the quantity, okay, the energy density, okay, for the material A is higher than the material B, okay, since the average stress is more, okay, and E is more or less, the epsilon, the strain is more or less comparable, okay. So, if we compare the material in sense of the total volume, okay, then material A is more efficient than the material B, okay. So, energy density, okay, we calculated the energy absorption per unit, the total energy absorbed per unit volume, okay, that was given by EV. And by looking into the two numbers, we can say that if we look into the EV criteria, the material A is more efficient than the material B, okay. So, moving ahead, so in second part we are asked to compute the specific energy of the both, okay. So, in first case the energy density was asked, that is the total energy divided by per unit volume. In the second case the specific energy is asked, that is the total energy divided per unit mass. So, the total energy, specific energy per unit mass is given by this expression, and we already have calculated the volumetric energy, okay, and then we are using it to calculate the specific energy. So, the specific energy for the first quantity is given by the volumetric energy divided by the density, okay. So, this is one expression and the two expression. So, if we look into the efficiency, if we compare the mass, then material A is better. If you look into the volumetric efficiency also, the mass A is again better, okay. We come back here, okay. So, first we calculated the total energy divided by per unit volume, okay, that is the energy density, okay. So, in this case we found out that the material A is superior than the material B. Then we calculated the total energy per unit mass, and here also we find out that the material A is efficient than the material B. So, in both the cases we found out that the material A is superior than the material B. So, we use the specific energy and the volumetric energy to compare the two scenarios, okay. So, we will stop here and we will continue in the next class. Thank you.